Ilya Radzahovsky. I'm a professor here in the physics department, and as your host, it gives me a great pleasure to welcome you here and to introduce tonight's speaker. Before I do that, I want to give you some background on what this lecture is about, and also its connection to what's going on in the physics department. Namely, some of you know, every July we hold an advanced study institute, so-called Boulder Summer School for Condensed Matter and Materials Physics here. It involves inviting 65 of best and brightest graduate and PhD students and postdocs from all over the world to come visit us here and spend 4 weeks and learn the frontiers of physics on the current topic of the school. So maybe we can have a show of hands from the best and brightest. Let's hear you. Who's here? There's some of you here, so so they're going to be at school just begun, and it's on the subject of the public lecture as well. It's on discussion of quantum mechanics and dynamics in quantum systems, quantum many-body systems, something that tonight's speaker will talk about. So the school is supported, Boulder Summer School is supported by National Science Foundation. And so this public lecture is an attempt to outreach to the greater Boulder and Denver area, and it's really your tax dollars at work. So tonight's speaker certainly needs no introduction in physics circles. His name is Professor Terry Giamarchi. He's visiting us from Geneva. He's a world expert on quantum many-body systems, strongly interacting many-body systems, but particularly when it has to do with low-dimensional systems like quantum wires. And some of that he may touch upon in his lecture. He is well known for numerous seminal papers. He has, to his name, he has over 200 publications. In our circles, he's also known for really wonderful text that he wrote on the subject of low-dimensional quantum many-body systems. He was educated in Paris and worked in Paris as a member of CNRS for over 20 years. But in the last 10 years, he moved to Geneva, where he's a professor at the University of Geneva. The subject of low-dimensional quantum many-body systems is kind of subtle and tricky, and so not everybody can survive and figure out how to excel in the subject, so it takes a special person. And Terry is one of those people, and part of the lecture is to show you how he has these special skills, and those skills are his ability to do magic. And so this is exactly the kind of skill that's required to be able to operate in this one-dimensional world of quantum many-body physics. So without further ado, let me introduce Terry, and he's going to tell you about magic and how it meets quantum mechanics. So please join me in welcoming Terry.
Thank you very much. Is the mic on? Can you hear me?
No,
it's not on. So
it should be light, green light.
Let's try it. I don't see any light, so that's the first magic part of the evening. Now it's better? Yeah. No? Okay, so let me bring it closer maybe to my mouth, and we'll get started. Now can you hear me better? Yes. Super. Okay, so first, thank you, Leo, for the kind introduction, and thank to all of you to have come to this slightly unusual public lecture, because as you saw in the title, it's not only about physics, but I'll talk a little bit about magic, and especially card magic, and you will see why this is my Jekyll and Hyde side. I like both physics and magic. Before I start the lecture per se, I need to thank several people who have directly or indirectly contributed to this lecture. I want to first thank Jean-François Dard and Anne Papillot, who made some of the beautiful images you saw on the flyer. They have a very beautiful site where they interviewed physicists, mathematicians, biologists. It's unfortunately mostly in French for the moment, but it's slowly translated to English. I highly recommend it. It's a very beautiful and aesthetic site. They have some books, again, interviews of scientists, which give you a glimpse in the mind of scientists, which are very interesting and nice. Some research network in Switzerland to which I belong, who provided some of the image I will show you, and some outreach part of this network which try to show high school kids a little bit how physics is done. And also especially Dominique and Alessandra Duvivier, who are extraordinary magicians and even more extraordinary card magicians, and who taught me all I know about magic, and of course all the clumsiness is mine and they cannot be held responsible for my clumsiness. They are also the owner of the oldest magic store in Paris, and if you are interested in magic, I highly recommend a visit to their website. And finally, last but not least, the University of Colorado at Boulder, and especially Michael Tomasa, Xiao Lin, and Leo Ratiowski, who helped a lot in preparing this lecture and the material that goes around. And as Leo was mentioning, one of the reasons I'm here is because there is every summer a fantastic summer school taking place in Boulder. The one this summer has a weird title and even weirder content that I will not try to explain during these lectures, but maybe by the end you will have some idea of what we are trying to do. So what I would like to do is first try to tell you about physicists. Maybe I'll switch off the lights so that you can see the screen a little bit better. Because one thing you realize very rapidly when you're a physicist, and I realize that even more by my contacts with the magic community, is that people have absolutely no idea of what a physicist is. This is the traditional vision of a physicist. It's called Professor Cosinus, cosine in English, if you want. It's a first cartoon of the beginning of the 1st century. Closer to us, we have Professor Calculus from Hergé, and it goes down from there. You have Professor Zarkov from Flash Gordon. You notice the lab coat. It's very respectable if you have a lab coat or something intelligent with a lab coat. And here is the European equivalent of Flash Gordon. It's called Luc Orion. I let you guess in this picture who is the physicist. The pipe seems to be also some essential ingredient for physicists. This is Professor Mortimer from Edgar P. Jacobs from Blake and Mortimer Adventure. Here you have Bruce Banner, who tempered a little bit too much in gamma radiation. Note the lab coat again, which makes its appearance. Sheldon Cooper, in which you can, if you're a physicist, recognize several of your colleagues. So the main message of this is just to say that when you discuss with a person at random, the general impression of what the physicist is and what he's doing is that, or he or she of course, is that the person is a kind of Martian who does stuff, and when you discuss with people and you tell, you know, in a conversation, they tell you, oh, what are you doing? I'm doing physics. It's very interesting, and I was very bad in math at school. And that's a conversation. Conversation starts here, and you know, nobody really knows what we are doing. So tonight I would like to explain to you a little bit what we are doing. What is our job? What do we spend all the days doing? You know, where your tax dollars are going, okay, things like this. But more importantly, what do we do? Any resemblance of the midsection of this character is purely coincidental. Another community that people don't know very well is the community of magicians. Of course, you all heard about magicians, but usually this is the vision of a magician. And again, it goes from bad to worse. You get that. The physicist had the lab coat. The magician has the magic wand, which is usually here a cane, and a cape, and a hat. That seems to be the official attire of a magician. The beard can be also part of the attire. No, the magic wand is still there, and the hat under another form. The hat is usually supposedly used to pull the wabbit. Magicians are supposed to have various kinds of animals which are floating around them. Again, that doesn't correspond to the truth. Physicists, I will not show you real physicists because they are hidden in the room here. You can check your neighbor, are you a physicist? But I will show you real magicians, and they have nothing to do with this type of caricature that you see here. Here is probably the best magician of the 20th century. His name is Vernon, and he was mostly based in Los Angeles. He's very versatile magician, card magic, other type of magic. Okay, he has a mustache, but he has no beard. So. Okay. The beard can be here. The name of this character is Larry Jennings. Is one of the best card magicians. He passed away about 10 years ago. Closer to us, somebody I'm sure you've seen in movies, but you didn't know he's a magician because he loves to play small roles in movies where he's not doing any magic at all. His name is Ricky Jay, and he's probably the best living card magician on the planet. He has a beard, okay. But I just want to emphasize that you don't need to have a beard to be a magician. And here is an example. One of the very few, unfortunately, I would say that's something that magic and physics share, is that there is a very disproportionate number of male and female magicians and physicists, and it's something we really need to work on collectively to correct in both communities. Okay, so after this presentation of the various types of magicians and physicists, well, let me move to the subject of what I want to tell, which is what is the job of a physicist? Because it's not so clear. What do physicists do? They work on stuff. They do research. For physicists, I'm sure your grandmother asked you one time, what are you doing? And you say, I'm doing research. Ah, and did you find it? Not really. Okay, so I'll try to explain what the physicist does and what the magician does by using essentially cards, because I'm a card magician. And it's not very easy to do card tricks for such a big audience, because this is something that physics and magic share. There are various kinds of physics and there are various kinds of magic. There is small tabletop physics, there is small tabletop magic, it's called close-up magic. There is parlor magic, where the magician is usually 1 or 2 meters away from a small group. And there is stage magic, which is big magic, where you have a whole room like this, and then you take a woman, you sew it in half, and whatever. And you have big physics, which is CERN, accelerators, and things like this. So you start seeing that we share a lot between physicist and magician. So here we are really on the other side of intimacy. And the only way I can show you card magic is thanks to this projector here. So watch carefully the screen. For those who are close, you can probably see the mat. I apologize if these things on the table disturb your line of vision, but I will need them for the rest of the lecture. So it's probably better to watch directly on the screen. The job of a physicist is like the job of a magician, and it's to understand the magic tricks that nature is playing on us, and if possible, to invent new ones. The job of a magician is to invent new magic tricks. And I'll try to illustrate that by using the tools of a magician. A physicist has different tools, we'll come to them, and the tools of a magician is a deck of cards here that I will try to use to show you the type of magic tricks that nature is able to play on us. So when you deal with nature, you have to look carefully, because sometimes something remarkable happens. And when this happens, you need to try to understand why it happened, what caused it, and then, if possible, reproduce it, or be on the lookout for even more fantastic things which could happen. Because if you look carefully, then sometimes it requires skill, sometimes just luck does it. But the goal of a physicist is the same than the goal of a magician, to understand the tricks that nature is playing and, again, to invent new ones. Even when non-interesting things are happening, then it usually just takes a little bit of twisting to get a nice miracle. And once you have understood, when you're a physicist, and once you have understood what tricks nature is able to play on us, then what you can do is usually make them faster and make them better. And that is the job of a physicist. So let me continue a little bit with the presentation, because what I try to tell you in these few words is that the physicist is an artist, like any other artist. We are not supposed to manufacture a product. We are not supposed to fulfill an honest job in society, more or less. What we are supposed to do is, as I said, try to understand with our skills what nature is throwing at us and try then to perfect this. And that's the same job that an artist here is doing, whom you probably all know. And an artist means a lot of skill. Here, playing the violin, which requires a lot of training, and in physics, it's the same thing. Except the skill you need are not something you have in your fingers, but for example, something which consists in assembling equipment here, or thinking about an experiment. Here is an optical table in the group of Tillman Eslinger in Zurich. They are practically identical things here in Boulder, since this is a high place for a field of physics that people call quantum optics. And the talents of artists are varied. There are many, many ways it can express itself. It can be a skill at playing music, it can be a skill at singing, at dancing. Same thing in physics. The skill can be in devising an experiment, or it can be a skill in dealing with equations, with numbers, with abstract concepts. But this is just a tool. Again, this is a tool. The goal is to understand the magic tricks that nature is throwing at us. Here is Fischer Dieskau, one of the best singers of the 20th century. And again, some other physicists have other skills. They know how to use supercomputer, how to devise programs that will help understand the magic tricks that nature is throwing at us. Now, usually when it's usual artists, the contact with the person in the street is relatively easy. We are a little bit more abstract, maybe, but this is not uncommon. If you look at art, there are sometimes forms of arts, like modern painting, which sometimes require a little bit of knowledge. So here is a painting by Salvador Dali, for example, which require a little bit of knowledge from the public to be able to appreciate it. And for my part, for example, I must say that modern art leaves me usually quite, let's say, unresponsive. So we usually suffer from this lack of contact, and that's why there are also these public lectures to try maybe to make the public more aware of what we can do. Okay, so I just told you that our goal is to understand nature's trick. But you could say, how? How will you do it? Of course, you could do it with a big machine, you could do it with a small machine, you could do it with equation. But that's not the point. The point is not what machine you use, but what method you use. And there is something which we all use, which is known as scientific method. And it's remarkable to notice that we live in a world which is highly technological. You all have a cell phone, which is a concentrate of technology. You all surf on the web. But it's remarkable to see how little the scientific method is known by people. The idea is very simple. You make a prediction, and then you test it. You test in something called an experiment whether it works. And if it doesn't work, your prediction goes to the garbage can. If I take a rock and I drop it, it falls. I repeat the experiment, it falls. I repeat the experiment, it falls. I can say, I view the world as every time I leave a rock, it goes down. Think in everyday life and try to apply the same method. Someone lied to you 10 times. What is the probability that the 11th time the person will lie to you? Well, I guess politicians would be in trouble if we were relying on the scientific method too much. So I will try to illustrate with, again, a card trick how the scientific method works. Because you see, the physicists, they are sometimes the magician, and they are sometimes the spectators. And nature is the magician. So here, you will be the physicist, and I will be nature, if you want, and I'll do a magic trick for you, and you will tell me how it's done. Now, I don't want to debunk a serious magic trick, because I think it's spoiling the wonder, so I've chosen a cheat, which is something probably many of you know, which is called the 3 cards Monty. It's a real cheat which is practiced by people in the street, which is done with 3 aces. I don't know if you can see, 2 red aces and 1 black ace. And that's a cheat. Don't play. This is not a game. This is really people wanting to take your money away. Okay? But here we will use it as some fantastic experiment, and you will try to do it. So I will do something that the people on the street do not do, which is I'll do always the same moves, because nature doesn't change. When you leave the rock, it falls down, and not on Monday, and falls up on Tuesday, and whatever. So here, I'll follow the moves. So the moves is, in the street, you have to follow the ace of spades. Okay? So imagine you have some compound, some object, and you do some measurement. You measure the resistance of the thing, and usually what happens is that when you do this very complicated experiment, you find some result. Here, the ace of spades is here. And again, you will probably see better if you look at the screen. Okay? And it works all the time. So far, so good. You do your experiment. I'll do it a little bit faster. Hop, hop, hop. And the experiment always gives the result that the ace of spades is on the right. And then one day, someone synthesizes a new compound and does the same experiment, measures the resistivity, for example, of the compound, and that's the same experiment, and this time, some different result happen. And you have to understand why. Now, of course, if it's a card trick, you would imagine you can do everything. You can come and turn the card, but you cannot do that. When you see a magic trick, you're not jumping on the magician and turning the cards and whatever. Well, in physics, you cannot either. There are things you can do, and there are things you cannot do. You cannot look inside the matter and see every individual atom in the matter. So there are limitations. You can observe some things, but not observe others. And of course, this depends on your equipment, this depends on your imagination, and so on and so forth. So here, let's try. What would you suggest me to change in the experiment? So you will try changing the experiment to try to know how I do it. For example, do you think that I cheat in the second part?
No.
No? How could you decide that?
I saw you throw the card before you.
Yeah, so keep it for the moment. So, how could you decide that? For example, if you want to know if it's the second part, then imagine you have a high-speed camera. You will take a slow motion picture of this, and then you will see me go very, very slowly and check that indeed it's not in the second part that I cheated. And you say, but if you have a high-speed camera, why don't you use it for the first part too? Well, maybe you can't. Like in experiment, there are things, again, you can do and things you cannot do. So we established here that for this trick, it's not when I shuffle the cards on the table. And indeed, then it means that it's only when I throw the cards on the table that I am cheating. So, for example, when I do this, that's it. The ace of spades is not here. And the way I did it, and people on this side are in a much better situation than people on this side to decide, so don't feel bad if you didn't catch it, is the fact that, and that's the way people in the street cheat you about it, because they want you to bet money on it, is that instead of throwing the ace of spade, in fact, when you do this cheat, what you do, you throw the second card, you throw the ace of spades. But now, okay, we've understood, so we are very happy to have understood this. So now we can do what physicists do, we can do a prediction. Because if I now have this theory that indeed I throw the ace of hearts here, then it means that the ace of spade is here. So it means when I do the move, not only I know it's not here, but I know it's here. And I can make the prediction that the ace of spade will be here. So now I go back to my experimental colleague and I tell him, okay, do the experiment, and you will see that the ace of spade is in the middle. And if it works, my theory is right, and I get the Nobel Prize. Maybe not for that. Okay? And then everything works well. Up to a day where someone comes to see you and say, I've done the experiment, the ace of hearts is here, but here I have the ace of diamonds. So your theory is wrong, doesn't work. And then you have to decide. Again, scientific method. How do you decide whether you're wrong or right? Well, you ask another experimentalist to do the same experiment. And if everybody finds this, then you're wrong. Because although you predicted correctly that the ace of hearts should not be there, the rest doesn't work. And if the rest doesn't work, your theory goes to the garbage can. Or your experimentalist friend is a bad experimentalist. This happens. Instead of measuring something, he's measuring the electric noise coming from the coffee machine of the next building. Or things like this. This happened. I won't quote names, or I won't, but this happens. Coffee is an essential part of physics now. And so again, you have to check whether this is an accident, and if you redo the experiment, then you get back the result where the ace of spades is in the middle. If it's repeatedly not in the middle, then your initial theory was wrong or incomplete. You have to complete it. When Einstein came and explained that the universe is described by general relativity, it doesn't mean Newton was wrong. It just means that Newton only understood part of the truth. And then you add another layer to the truth. So for example, here, the theory is not wrong. It's just that I cheat twice. And instead of, I throw the ace of hearts here, but instead of doing this and that, which will put the ace of spade in the middle, I just use the fact that I can go a little bit quickly, and I do this, and I put the ace of diamond in the middle, which then, when I move the cards, will put me the ace of heart here, and the ace of diamond. So you see by this very, very simple magic trick, an example, how nature is throwing things at us and trying to hide the truth. There are objects, like the objects which are in this little cup here, we still don't know how they work. We know we can make them work, but we don't know what is the mechanism that really makes them work. And the reason we don't know is because they are very complex, and we cannot go down inside and decide what is making them really work. Okay, so let's continue a little bit, because now you have a better idea of what is our job. So, you know, we play with cards all days. No, sorry, that's, we play with instruments which are doing the same thing than what you did with your eyes. Your eyes are fantastic instruments. And then, using this instrument, we try to understand how nature is working. And I would like to continue and describe to you one of the most beautiful class of tricks that nature has played on us in, let's say, since a century or so. Well, it played it since a very long time, but we didn't realize it. And this goes by the name of quantum mechanics. And this is a very complicated theory, but here I will try to, of course, make it as simple as possible, and also as close to cards as possible. So let me try to give you the basis of quantum mechanics. In the real world, we know that if an object is there, it's there. If I put a card here, it's there. And You're all familiar with that. Sometimes you don't know where an object is. If you have socks, for example, you can put it in one drawer, and then you open all the drawer, where's my sock, where's my sock, and finally you open the drawer where your sock is, but at the end it's because you don't know, but your sock is really at this place. Now, of course, this worked well for a while, and then people realized that there were problems, that there were, for example, cases where objects were not really where people were expecting them, and this theory had to be modified, had to be extended, and matter was not behaving the way it was supposed to be. And then came this crazy guy, whose name is a magic trick by itself, because his name is Louis de Broglie, but it's pronounced Louis de Broglie. It has a completely different pronunciation than the spelling, but except for that, the guy had a completely crazy idea to say, in fact, matter is not matter. I can touch it, damn it, but it's waves. Now, what does it mean? You all know waves, you have seen water waves, the surface of water. So what this guy came with an idea is to say, okay, let's assume that the whole universe is described by a wave. When the water is high, if you want, not water, but when the wave is high, it means there is matter at distance. And when the wave is low, it means there is no matter. So this can move and go up and down and change, and even worse than that. And I promise it's the only graph I will show in this lecture. The wave is not telling you that there is matter, but it tells you that it might be matter at that point. So to know that, you have to throw a dice, and if you win, you get the matter. So for example, if the wave is like this, so you get a kind of tsunami here, which the wave is very high here and zero here, it just says that you have a lot of chance to find your card at this position, and zero chance to find your card at this position. So far, so good. It's not very different from saying, I take a card and I put it here. Okay, there is a wave which is doing that. Where it becomes really weird is the fact that the wave can do something like this. And then what it tells you is that you have 50% chance to find your card here, and 50% chance to find your card there. Now you will tell me, I know the problem, because I have socks. And I have 50% chance to put the socks in this drawer, and 50% chance, no, it's not the same thing. You don't remember in which drawer is your sock, but the sock is 100% in one of the drawers. Here, it's not the case. There is a kind of phantom card. I'm doing it with card, it's more human than with cats. Usually, quantum mechanics, they put the poor cat in a box and they tell you it's alive or dead or whatever. But I do it with card. So, essentially, it tells you that you have 50% chance to find your card here, and 50% chance to find your card there. And until you look, the card is in both places at the same time, which is very weird, and which we don't believe because we have been used to have damned objects which are at a given position at a given time, and not objects which can be in two positions or two states at the same time. And the reason why it's that way is because we learn by our senses, and we have been using big objects, and with big objects we have learned that an object is where we put it. It would be interesting to train a child and train the child in the quantum world. Of course, this is difficult, but maybe they would develop a completely different intuition. I wonder if kids with iPads, for example, will believe that by just passing your finger on a wall, you can generate paint. But that's the same idea. Here, we believe that if we put an object here, it will stay there. I'll try to twist a little bit your intuition using these two cards, okay? Because cards are nice objects that allow me to illustrate this concept of quantum mechanics. So let me try to do a machine which will bring you to the quantum world. Okay, let's try it. I need a very precise machine, and that's very difficult for me because I'm a theorist. I'm normally using equations, and here I'm trying to do an experiment, so this is exceedingly difficult for me. I'm sorry. can I ask someone, can you bend the card, but in the other direction, along this direction? The big direction, yes. Well, the other side, but that's okay. You see, that way if it doesn't work, I can put the blame on him. Thank you very much. Okay, so because with this, I can construct a little quantum machine, if I manage to do it, because you see, the point is that a card like this is only in two states. You either see the inside, or the outside of the card. Here, you see the inside of the card. You see the face of the card. And if it was a classical card, it would stay that way. But now, we're in the quantum world. So, let's see. You see the other side of the card. So an object can be in two states at the same time. And that's really highly unusual. So, now let's try to do it again. Let me try to do it again. Now, of course, if it was the classical world, then I could not do that and show you the two sides of the object at the same time. Or even worse, I could not do that and show you that the card is really in two states at the same time. But you see, this is but an illusion because the cards are classical objects. So they can only be in one state at the same time. So if you leave them too much like this, then they will forever stay trapped here on the inside and here on the outside. But this is not the case for quantum mechanics. Quantum mechanics, this is a real object. And you get these phantom cards, which are there until you look. And when you look, your cards get there or get there. And that produces very bizarre effects, which we are not used to in our classical world. Now you could tell me why I've never seen that. Well, if you want the answer, ask to these two guys, Serge Haroche in France and David Weinland here in Boulder, who got last year Nobel Prize to explain how you go from the tiny, tiny object of the quantum world to the macroscopic objects of the real world. And how is it that you see or you don't see these bizarre effects? So let me try to, oh, by the way, that's something I wanted to mention. I just performed for you is known under the name of card war, and here are the people who invented the tricks. Because in magic, it's like in physics. When you do something good, you get your name attached. So how can I test this crazy idea? After all, this idea of De Broglie and then people who followed, oh, sorry, no, I should put it back. People who followed, like Niels Bohr, Werner Heisenberg, Erwin Schrödinger, who are the founders of quantum mechanics. Why is this idea that matter is a wave not on the front page of the National Enquirer with Elvis is alive and whatever? How can I decide that it's not completely nice? The answer is the thing we did before. Do an experiment. Check. Test it. And the way to test it, I will try to introduce you to it, is something called the double slit experiment. It's very simple. You take a wall, and you put two holes in it, and then you take a place here where you can measure. So for example, imagine here you have a machine gun, which is shooting bullets. Then the only place where the bullets can go through is through the holes. And let's say here you have sandboxes, which count the number of bullets which arrive at one point. If I have objects which are matter, then the only place where I can collect bullets are at these very special places here on the wall, because the rest will not go through. This trajectory cannot happen, this trajectory cannot happen, and so on. Now, okay, some bullet might hit the wall here, so I can get a little bit more here, or a little bit more here, but that's the only place where I count something. So I should see essentially a high number of objects here, a high number of objects here, and nothing in between. What if I have waves? If I have waves, then what happens, and you saw this regularly in your bathtub, is that if you have a little place like this, a little opening, then the wave which arrives will sort of radiate from the opening, and then they will mix. So the waves which are created by these two holes will mix here, and the maxima of one wave can coincide with the maxima of the other wave, so they go even higher, or it can be the opposite. And then they just cancel. So if you work out what happens for this object, then you will see that the wave will cancel and add periodically, and essentially on this place, if you measure where you get a lot of amplitude of motion for the wave, you should see a regular alternation of a lot of wave, no wave, a lot of amplitude, no amplitude, a lot of amplitude, no amplitude. So something very different from the two places here where you would collect something. So this is a very clear experiment. If you do it, either you see the first case, and then the boy should be sent to a lunatic asylum, or you see the second, and then he should be given a Nobel Prize. Since I show you he already got one, you know the answer. But let me show you the experiment, because it's a very beautiful experiment. It was done by the late Akira Tonomura in Japan. The guy developed a fantastic apparatus that I will not show you, which is called a Lorentz force microscope, which is something which can allow to do fantastic things. And here he used it in a very simple way. So I have my machine gun here, which is shooting not bullets, but which is shooting electrons, which are the little grain of matter which carry the charge that allow to get electrical current in the room. And then he has a charge rod here, which separates the path of the electrons into two half paths, just like our two slits. And then he has a detector, which tells you when an electron is hitting here, the detector. It's a little bit the same principle than the old TVs. You know, the one before we had the liquid crystal screens, which take a lot of space because there was a cannon sending electrons, which were smashing on the detector, which was the screen. Okay. And then you just look at what you observe on the screen, and here is the result. So let me start the film, if it accepts to start. Okay, so you see here one electron has a 4, a 5th. So you say, okay, the boy is wrong. I see electrons as matter, it's not waves. But you see that something is not working well, because they are all over the place. They are not just concentrating on two specific positions on the screen. So although the electrons arrive one by one, as they should, they don't obey the classical trajectory that an electron or a bullet for that occasion would have, which is sort of going straight and hitting always the same place. Here is the film passed a little bit faster and faster, more electrons, more hits, and so on and so forth. And you see that something seems to emerge. Here is again faster and faster, more electrons, more. And now you see that there are regions which seem to be brighter. There is more matter here, which has reached the detector, less matter here, which has reached the detector. And you see here reconstructed exactly the pattern that you would expect from the waves, which shows you that all matter that surrounds us is both matter and wave. But this is not something that you could understand by the normal world in which we are used to, where an object is an object, and if I throw it, it goes straight. Okay. Now, there is something which is even more amazing, and I'll try to do the demonstration. I think we can switch now from the camera which is showing the card magic tricks to another camera which will show the physics magic trick. Okay, so quantum mechanics allows you to get very weird objects, which are this type of objects, which seem totally innocuous. This is little dark, it's not something you swallow for your health. And this system have very weird properties. The point is that if you want to evidence the weird property of this object, you have to cool them down. And when I say cool them down, I mean really cool them down. And to cool them down, we use here some fluid, and this fluid is air. So you're all used to see air in the room, and you know that air is a gas. Well, it's a gas because at the ambient temperature, which sorry, I will talk in Celsius degrees. I hope someone can help me convert to Fahrenheit because my brain power is not fast enough to really make it in real time. We all know that everything in the world exists depending on the temperature in different states. Water, for example, you're very well used to have water as a liquid. And this is between 0 Celsius and 100 Celsius. Okay? If you cool down water below 0 Celsius, you get a block of ice. So you get a solid. And if you boil water on your oven, you get gas. You get vaporized water. Well, the air in the room, it's exactly the same thing. At this temperature, it is a gas. If I cool it down, it will become a liquid, which is in this bottle. And if I cool it down even further, it will become a solid. Okay? So what I have here is liquid air. Okay? I'm slightly lying to you because the air is made of 2 elements, nitrogen and oxygen. And so essentially only the nitrogen has been cooled down here. So what I have is liquid nitrogen, but this is liquid air. When I put it in the recipient, I don't know if you see it here, but it's boiling. It's boiling because for the air, the recipient is like a boiling oven. It's at the temperature, it's like when you put water on an electric stove, you make it boil. This is at the temperature which is about minus 200 Celsius, which should be about minus 400 Fahrenheit, if I'm not wrong. Leo, you can do the calculation meanwhile. And so this is something which is extremely cold, a liquid which is extremely cold. And of course, I will pour a lot in the recipient here so that it cools the recipient and then it will stop boiling. Okay? Now, the fact that it's so cold has, of course, very interesting and funny properties. Don't dip your finger in it because otherwise... So here is, for example, some rubber tube. And you all know rubber tube, it's very flexible. But if you put it in the cold, then usually what happens is what happens to your finger if you go to the mountains and you don't wear gloves. It's exactly the same principle. I don't have enough strength, but with a hammer I could break it. Okay? So that's rubber when it's put at very low temperatures, and then we'll just let it warm and you will see that it will get, let's say, flexible again. Now, let me take a balloon. What do you think will happen if I take the balloon and I put it in the... what? Yes?
Shrink?
Yes, it will shrink. Because the only thing that maintains this balloon with its shape is the fact that the air that I have blown up inside is pushing the air which is outside. If I cool the air inside, it will just contract. And then my balloon will deflate. So let's see. Again, let's do the experiment. Maybe I'm bullshitting you. Here's my balloon. Now it warms up. It warms up, and then because it warms up, the air inside is getting back to its original state and is pushing against the envelope of the balloon, and the balloon recovers, recovers the, I was afraid of losing 1 or 2 fingers in the process. That's why I did the magic tricks before, but never Okay, so there are other experiments, but since the time is getting short, I will try to do it directly with the objects here. So what I have here are these objects, which are called superconductors, and we will see why in a moment. And I have a little magnet here. So this is a regular fridge magnet. And what I'll do, I'll put the liquid nitrogen, which again is extremely cold, it's minus 200 Celsius about, here, to cool down this object. I don't know if you see it, there are little balls of liquid nitrogen which are on the table. And you could ask why, and I don't know if you did this experiment with a very hot frying pan. When you put a little bit of water in it, you see a drop of water which is moving on the frying pan. The reason is that the heat vaporizes the water below, and it makes like a little cushion of air, which allow the drop of water to slide, if you want, without friction. Here it's the same with the liquid nitrogen, in the sense that if I drop it on a very hot surface, which is the floor, first you notice that there is no liquid, it disappears. But if you look carefully, there will be a lot of little drops of liquid nitrogen that will move everywhere because they are floating on a little cushion of air. Okay, while I was talking, this was getting colder, but now you see it has evaporated all the liquid nitrogen. So let me try to put more until it's cold. And then we'll see if it's working. If it's not working, I'll try to show you a movie. Didn't you like it when your whatever high school teacher, chemistry teacher tells you it will turn red and poof, it turns blue? It's totally ridiculous. Okay, so let's see if they are cold enough. As long as it's boiling, it means they are not cold enough. They are sort of acting as an iron rod, which would be put in red hot stuff, which would be put in the water, for example. Okay, let's get them getting colder and colder. So I'm brewing my saucer brew here. Let's see if I can already. Yeah, I think you see it. Maybe not because it's boiling too much. Let's try it again. There are too much, it's boiling too much, so too close. You see the magnet here? It's not touching the object. I don't know if I can focus on it. I'm trying to bring it closer. It's cold. Yeah, here it is. The magnet is levitating above the objects. Yeah, let's try again. I'll try it in the center. There you are. I can even probably make it rotate. You see the little white spot on the magnet?
It's too small.
Yeah, when it will stop boiling, it should be a little bit better. So the magnet here is not touching at all the object. So it's levitating above the black acid. So what we've realized here is some fantastic magic levitation experiment. Let me maybe show it to you a little bit more obvious here. So here it's the inverted experiment than the one I did here. The mysterious compound is here, and the magnet is above. Here, the magnets are here, and the mysterious compound is above. But that's the same idea, that this object that floats above a magnet. Now, I don't know if you tried, because of course the question is that it's a beautiful magic trick. I swear there are no ropes, no hidden tricks or whatever, and if you get closer you can look at the thing which is here, or I think here you view it now very clearly, that you have the black compound here, and you get a sizable distance here between the magnet and the black compound. Now you could say, oh, that's easy. I know, with magnets I can make things levitate. Well, I don't know if you tried with two magnets. Try it. You will do it, and then suddenly the magnet will turn and schlack, you will get glued on the other magnet. So there is something here which is different, which is happening. And I can show you a little movie here, which was done in the Outreach network, where you do a little train which contains this mysterious pastille, and then you make it levitate on a rail which is made of magnets. And here is again the same object. There are many of these black, oh, here, look, it's very beautiful. Now it's white, you can see it here, it's really levitating. And you can do even worse, and you will see in a second. You notice the little balls which are running away. Now you pull it down and it levitates, and here is the temperature, minus about 200. And look at what the guy is doing. He's turning it, and it doesn't fall. So it's not just levitating, but it's sort of trapped at a certain distance away from the magnet. Nice magic trick, yeah? How does it work? How does it work? And that's something that people call superconductivity. And the trick was discovered a long time ago by two German gentlemen, Meissner and Oschenfeld, in 1933. And it was not too long after that two other German gentlemen, the London brothers, who escaped Germany because of Nazi persecutions and came to work at Duke University here in the US, understood. They didn't understand what in this mysterious compound is causing the effect, but they understood that the only way it can work is, of course, if this object is like a magnet. But a magnet that would sort of change its polarity depending on which side of the magnet you're presenting to it. So it's a kind of intelligent magnet which is determining how it should behave. And in fact, it's not really a magnet, it's an electromagnet. And they understood that there are currents that are circulating inside the compound. Okay? Just like if you want to do an electromagnet, you take a battery and you put wires around some metallic object here, and then if you do this, you will get the equivalent of a fridge magnet, which has a north pole and a south pole, like a little compass. And depending on the sign of the battery, the north pole is here, or the north pole is on the other side. You notice that here it's exactly the same principle, except there is no battery. And the currents are turning, but this is crazy. You know that you cannot have currents turning inside a wire without losing the current. It just heats, dissipates, and stops. And essentially, it tells you that it's only possible if this object can also transport current without any loss. So if you pass a current through it, there is no heating, no dissipation of the current. So it's a perfect conductor. And that's why they are called superconductor. Super is really nice. And the way it works is something which is very interesting. And this was a really tough trick to try. The first person who discovered this effect was looking for something else. So there is a certain level of serendipity in science, just like in magic, but that I won't explain. So here is the original curve, where he measured the resistance of the compound as a function of temperature, and so that the system transports current without dissipation. These were these two gentlemen, Camerlingones and Holst, and this was in 1911. And the thing was cracked by three other gentlemen, John Bardeen, Leo Cooper, and Bob Schrieffer, in 1957. It took 46 years of experiments, theories, to understand this magic trick that nature was playing to us. And the best and brightest tried it. You know, Feynman, Landau, Pauli, they all tried it, and they failed. And the people who understood the trick were these three people, John Bardeen, Leo Cooper, and Bob Schrieffer. So just to show you that sometimes it takes a little bit of time to understand the magic tricks that nature is throwing at us. We cannot always do it in 5 minutes like I showed you. Now, I would not explain how it's done, but I would like to finish this lecture How can I switch off the lights? Yeah, let's do it that way. By showing you that I showed you some example of the bizarre aspect of quantum mechanics. Oh, by the way, the explanation, it's again quantum mechanics. All the waves of the electrons that are in the material, when you cool the material sufficiently, they move coherently together. They all beat together. They make a kind of super wave. And then nothing can stop it. No dirt which is in the material, nothing can stop it. So this effect is quantum mechanics you can touch. It's quantum mechanics that you have really under your eyes. And this is because electrons are waves that this effect is possible. Otherwise it would be completely lost. I just want to show you something, which is that physicists are artists, and all artists leave you with something. When you get out of a concert, you get better. You have the memory of a memorable event or something. We usually cannot do that for you, but what we do is that sometimes, not always, and that's not what we are looking for, but sometimes what we do can really impact your life and change the world. Hopefully for the better, but that's to be decided. So I just want to show you that quantum mechanics, which is bizarre, which is weird, which is non-intuitive, you all have it in your pocket. You all are using it, and you don't know it. Because thanks to quantum mechanics, we understand what makes a conductor, and we understand how we can transform sand into a transistor, into a microchip. Microchip, they don't come from Intel or any other company. They do, of course, now. But the real place where this came from is a little laboratory in AT&T Bell Labs, where these three gentlemen, Shockley, John Bardeen, and Brattain. Oh, remember Bardeen? It's the same guy on the previous slide. He's the only physicist who got 2 Nobel Prizes. One for the transistor, which, you know, this is a magic wand, and really magic, because I can control my computer, which is also really magic, but which is working thanks to quantum mechanics, and thanks to these three gentlemen who try to understand and predict and invent a new magic trick, which was called a transistor. If you look at your telephone, whatever it is, it's a concentrate of quantum mechanics. The chips which make it work, they only work because of quantum mechanics. Worse, the little lights which are there on your phone, they don't work like the lamps which are there. They are called light-emitting diodes, and they are full quantum mechanics. They work with a principle which is deeply rooted in quantum mechanics. They are much more energy efficient than the normal lamps, and they are, of course, much more versatile. Not only the lamps, but also the CCD cameras. Every phone now has one, sometimes 2, to take pictures on one side and see your face at the same time on the other side. And this is, again, the reverse principle than the light-emitting diode, which is making this CCD camera work. And there was a Nobel Prize, by the way, which was awarded for the CCD camera. And when you couple a light which emits light with something which can transform the light into an electrical current, and you put an optical fiber in between, you get the world of technology of information in which we live today, and which would not be possible without this quantum mechanics. If I talk about superconductors, which is again quantum mechanics, it's a little bit maybe less in your life for the moment, but it's slowly getting there, because it can transport current without any loss. You have to realize that about 10 to 20% of the current which is produced is simply lost in transporting it from one place to the other. Which means if you have 5 power plants, you could save 1 by replacing the copper cables which are transporting currents by the superconducting cables here, which can transport it without dissipation. This is here, one single of this little superconducting cable can transport as much current as this big copper cable. And it's already there. In Albany, there is already superconducting cables which have been hooked to the network and which can be used to transport current in places where it would be difficult to pass normal copper cable. Of course, you need to cool down the objects. So here you see the system which produces the cryogeny, but except for that, this is something that is already now in production. Remember the little electromagnet that I told you, and the fact that these objects can behave as little electromagnets? Well, I mean, this can be used to levitate trains. In Shanghai, from the airport to the city, there is a levitating train which is using this principle. And there are prototypes in Japan. Of course, because there is no friction between the train and the, let's say, support, you can reach much higher speed than with conventional trains. It can also be used as a fantastic electromagnet because these cables do not dissipate, they do not generate heat. So all the energy can be used to produce magnetic field. So this can also be used to produce big magnetic fields that are useful in research. This is an image of the CERN accelerator, where in order to accelerate the particles and find the Higgs bosons and other big discoveries which are done there, they use superconducting magnets, there are 27 kilometers of this, not these compounds, but similar compounds, which are producing the magnetic fields that are necessary in the CERN. When you go to an hospital, which I hope not, but if it happens, there are so-called MRI, magnetic resonance imaging machines, which are producing non-invasive, non-destructive images of your body. The principle of the measurement, it's another story, is also quantum mechanics. But let me ignore the principle and just look at the machine. You need a gigantic magnetic field to do this measurement. This machine is a superconducting wire here, which is wrapped on itself. And what they do at the factory, they put the battery, they send the current in the wire, and then they loop the wire on itself. And because the current can turn without dissipation, it stays there forever. So this is a big fridge magnet, if you want, which doesn't require any power source except the one to maintain the cryogeny. And this is, again, thanks to quantum. So we are at the end of our trip in the world of quantum mechanics and magic. And I try to show you that, of course, magicians, this is a beautiful Bosch painting on one of the oldest form of magic, which is the cups and ball routine. So that the magician here and the spectators share the same love than physicists for magic tricks. We are sometimes magicians, we are sometimes spectators, always amazed by beautiful phenomena, using various techniques, cards or other instruments, to try to invent and devise new tricks, and especially try to explore this fantastic world of waves of quantum mechanics, which is a little bit frightening, but which has very much to offer. And on that, I will thank you for your attention. Are there questions? Yes?
Matter acting like waves on the law like Einstein.
I'm sorry, let me get closer.
Like matter moves in waves.
Yes.
That's not the law like Einstein said light can be either particle or wave. That's something completely different.
No, this is the same thing. So the inventors of quantum mechanics realized that, of course, our intuition or experience based on the macroscopic world was too primitive, and indeed, any object is both matter and wave. Now, Einstein is very interesting because although he contributed himself to this, at the end he was very much upset by this idea, and he tried to find alternative theories to quantum mechanics. And he failed miserably. And so far, although you can be emotionally disturbed by quantum mechanics, there is no experiment on Earth that disproves it. And it works. And it works even in situations where your intuition would really fail you. So the formalism, the technology that was developed to describe the world which surrounds us works better than our guts or intuition, because again, our guts are too much based on the macroscopic world, and we don't have enough intuition, but so far the equations work, and nobody has found the flow in quantum mechanics, even Einstein. Other questions? Okay. 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 Yes.
Will you explain the tricks of the cars?
Okay, so corresponding to explanation of tricks. In physics, a result only exists if it's shared with everybody, if it's reproduced by other labs, reproduced by other places. In magic, it's exactly the opposite. So I'll be happy to point you to magic sites, like I did. You can look at the website if you want to learn, but I will never explain a trick.
Thank you very much.
Thank you very much.
If you have any questions, Professor Mark again.